I mean, the analysis is actually it's a little bit more complicated than the truncation error analysis through Taylor series in finite difference, because you need to do these integrals. But the fundamental idea is exactly the same, right? You expand a function with Taylor series and figure out how big the truncation error is. You can do the same for the derivative at the interface, right? But like essentially, the idea for finite volume approximation is instead of approximating derivatives using the function values, we are approximating function values using function integrals or function averages. All right. Any questions so far? No?
No.
Okay. Right. So that's the first thing you need to check when you want to approximate interface value using the averages. The second thing you need to check is stability, right? It's always the accuracy and the stability are the two primary concerns when we get to how to approximate either ODE or PDEs. So stability, unfortunately, there is no generic way of doing this. It actually depends on the equation you are solving. And in just before the spring break, we have analyzed several different methods of finite volume, right? We have used we have used the central average method, which is second order accurate, but we found it to be pretty bad when you have a sharp discontinuity, right? We also use the upwinded scheme, right? I mean, upwinded scheme means if the solution is traveling towards the right, we are going to be looking at the left-sided average, the volume average on the left of the interface. And if the solution is moving towards the left, it's like the wind is blowing from the right, and we are going to be looking towards the right. We are going to be using the volume average, using the average on the right side of the interface as an approximation. Both are going to give us a first order approximation error. If you do this same truncation error analysis here, you're going to find out an upwinded scheme is going to be first order accurate, but it's actually going to give us a stable solution, right? On the contrary, if you use a downwind scheme, if you look at the wrong side, no matter what, your solution is going to blow up. So that's something I recall we did just before the spring break. Okay, and another thing we looked at before the spring break is that finite volume schemes can solve equations that are nonlinear, and we use the du dt plus u times du dx equal to 0 as a primary example. The primary difference between this equation and the previous equation is that it's nonlinear in the sense that the wave speed, right, the constant before the coefficient before the spatial derivative is not a constant, it's the solution itself. And therefore, the solution, the equation is nonlinear. And the solution can either go towards the left or go towards the right, depending on the value of the solution. So again, let's actually go to our previous lecture, and we have a finite volume demo. We coded up, right, this finite volume solution. Just to as a reminder, we set the number of grid points to 200, and our x, which is the grid points, right, that separates these 200 volumes, is going to be actually a 201 grid points that separates out these 200 volumes. Computed our delta x, and we had an initial solution. Okay, our initial solution is a sine wave. But in order for us to initialize our solution, we have to figure out the volume averages of the sine wave. And how did we compute the volume average? Well, we computed the volume average through the definition of the average by integrating the function, right? I mean, integral of a sine function is minus cosine. So this is the integral of the function from 0 to a grid point x. Our next line is to figure out, instead of the integral from 0 to that x, we are subtracting these integrals to get the integral from one grid point to the next grid point. Okay, and actually the integral is actually not only the integral but also the integral divided by delta x here. Right. So so here we already obtained the volume averages and we plotted them. So if we run this again, wrong section. It's actually closed. Wrong section. Yes, we are able to plot. How do I? Oh, don't know how do I move it. Okay. Anyway, so we're able to see these little volume averages as short lines. Okay, and then we solve the Burger's equation using ODE45 and plotted a contour of the solution. Okay, so if we run this, we would be plotting the contour, and if we run this, we would be actually plotting the solution as a function of time. So plotting animation. So let's see that.